Root locus analysis, example 14. So given the system shown, draw the root locus. In this one we have the root locus gain K and G all together as one block, and we have H, like in so many others, equal to 1, and that's our feedback path. So the first thing that we do in this problem is we find the open loop transfer function, and that's a pretty straightforward thing to do. It's simply going to be equal to K times G times H, and I'm just going to provide it to you. Notice that the only thing that's different than this and the block is that we haven't included the H in the block. Now in this case the H is equal to 1, so there's an understood H here, but I don't want you to get the impression that KGH is simply the forward path. It includes the forward path as well as the loop. So once we've done that, the thing that we note is that we have what looks like is going to be a fourth order system. So we've got an S plus 1, and then an S squared plus 4S plus 13. So that's a total of S to the fourth power. So there's going to be 4 poles in this system. And in this case, we also have no zeros, just like in the previous problem. So you can see that in this problem as well. Note that I don't show any work here. There's the S term. This is the S plus 1 pole. And then the S squared plus 4S plus 13 is the minus 2 plus or minus 3J term. Assumption here is that you can find that using the quadratic formula, which you should have no trouble doing. Now about the branches. So the branches, there's going to be 4 branches because we have 4 poles, so that's shown here. We also see that because we have no zeros, all of the branches will terminate at zeros at infinity. So I'm going to go ahead and we'll just draw the system, the pole zero map, and put those in. So -1, -2, -3, -4, 1J, 2J, 3J, and -1J, -2J, and -3J. So the first pole is at 0, so I'll go ahead and add that one. The next pole is at -1, it's right there. The third and fourth pole are at -2, so here's -2. And at plus and minus 3J. So there's plus 3J, and here's minus 3J. So right about there and there. So to find the branches, remember the branches only are going to be, finding these initial branches is just what's on the real axis. So if we look there, we can see, yes, there is going to be a branch there because there's an odd number of poles plus 0 to the right of the green branch. The fact that these two are close together, like all the other problems, means that there's actually 2 branches, and they're probably going to come together and then branch off on their own. What about here to the left of the -1 pole? The answer is no, because there's 2 poles, 1, 2, that are to the right of that branch. So that one does not exist. So we've got 4 poles, there's going to be 4 branches. There's an understood two branches between 0 and -1, that means that the other two branches are going to be for these two imaginary poles. Okay, so the next thing is to find the asymptotes, and just like the previous one, the finding the branches, I'll just provide that to you. You can see that we are showing the poles minus the zeros, so we've got a pole at 0, we've got a pole at -1, a pole. Now we got two imaginary poles, but we take the real parts of those poles. So we don't have to worry about the plus or minus 3j, but there are two poles, so -2 and -2. And then minus any zeros, and that's not applicable because there are no zeros. There's 4 poles minus 0 zeros, and so -1, -2, -2 is -5 over 4, so -1.25. So I'll go ahead and place that in as green, so that's going to be right about there is sigma sub A. And then the angle gamma, the asymptote angle, very similar thing. You'll notice I replaced the 2 pi with a 360. You can use whichever one you want, but we're going to divide plus or minus 180 plus or minus n 360 by 4 minus 0. And 180 divided by 4 is 45. 360 times n divided by 4 is going to be 90 times n. So when n equals 0, it's plus or minus 45. When n equals 1, it's plus or minus 135. And then it's going to keep repeating. So no need to put any more in. So we can write the asymptotes in now. They're 45 degrees, so there's going to be an asymptote up like that, an asymptote down like that. That's the plus or minus 45. The plus or minus 135 is going to be up like that and down like this. Basically a big dashed green X, and should be easy to draw the root locus based on this. So first of all, we've got a branch between 0 and -1. We haven't found the breakaway point, but it's going to be right in the middle. So this one's going to come to the right, this one's going to come to the left, and then they're going to break away, and they're at infinity. They're going to go tangent to these two lines, asymptote lines at negative and positive 45. It's hard to know which side that they will land on. Will they do this? Or will they do this on the other side of the asymptote? There's really no way to tell from this drawing how that will happen. One way is to find out the crossing point of the imaginary axis, and if it's down here or up here, that tells you which side they come out on. And that is possible to do mathematically, but when you're just drawing a rough root locus, it's probably of no consequence. So I'm just going to assume something like this, and something like this. That's a real ugly one. And it's also really difficult to know exactly what the root locus will look coming from these two, but obviously they're going to be tangential to these two asymptote lines. And it turns out that if we were to draw this using MATLAB, they do something like this. So what we can get from this diagram is that there are values of k where the root locus coming off of the 0 and the -1 pole, they're going to cross over to the right half plane, and that's a big no-no. We never want that to happen. But the two imaginary poles, they're always going to be to the left of the imaginary axis, regardless of the value of k. So those are safe all the time. So we just have to be concerned with these two root loci that are 0 and -1. So now that we've done that, let's go ahead and find the breakaway points, or at least I'll provide the expression for the breakaway points. And I'm just looking at method 1. And you see, I wanted to show you this formula. I mean, everything else is the same as previous problems except for these two. And I know I mentioned this before, but these are the imaginary poles. Whoops, imaginary poles. So remember, when we do the breakaway points, we're looking for a value that's on the real axis. So we don't worry about the imaginary parts of those two poles. We just worry about the real parts. So we have a pole at 0, -1, -2, and -2 from the vantage point of the real axis. And turns out that breakaway point is going to be right at -0.5, and here is our nice graph of this. And you can see, you know, that's sigma b, or sigma b breakaway. And that right there is sigma A. So that's an interesting looking root locus. And again, as k varies from 0 to infinity, the root locus does what you see in these black lines, and we're going to want to choose a k such that we don't go past these 2 points for a value of k. Anywhere on the anywhere on the real axis, so any values of k that put them right here is good. We probably don't want this pole right at 0. We want it to the left of 0. I would say probably, you know, point here and here would be the best, which would probably put these 2 poles here and here.